Hello and welcome to Tea Leaves Programming. Today we are programming like it's 1979, continuing Haskell for Dilettantes. Today we're looking at set 14a of the MOOC at Haskell.mooc.fi. We're going to do the last three exercises from this batch, number 6, 7, and 8. So our first exercise has to do with computing the XOR checksum of a byte string. So this chapter, or this part of this exercise set, is all about using libraries. We've got a byte string. If we're getting a list, can't we do something akin to a folder? So if we pull up the documentation for byte string, we can see that it has something that looks exactly like folder applied to a word 8, right? Because it's a byte string. Word 8, A to A byte string. All right, so I think we could just literally use this. Let's go ahead and drop that there. And this is B is our qualified. Is that right? Data byte string as B. Okay. So B.folder. And then what's our starting value? Our accumulator is going to be 0, I think, because we're going to be doing an XOR. And with XOR, we want exclusive OR. So 0 should be the identity value for that. We need a function there. That function, there's our whole, and you see that 1 to 2 to 3. We know that the type of XOR is A to A to A, so that should satisfy that XOR. Okay, let's take a moment. Point-free programming, tacit programming. I'm generally against it. I feel that it's mysterious. The idea behind tacit programming, as I understand it, is you're a nerd, I'm a nerd, and we like playing code golf and having as few lines as possible and as few names as possible. Because why would you need a name if you don't need it? It's much better for everything to be mysterious and inscrutable and for you to not be able to explain why your code works. So normally, I'm very against tacit programming. And the way I would write this under normal circumstances, right, would be something like this, right? Where this is our input byte string, here's our operation, here's our function, here's our accumulator, and this is the thing being operated on. Theoretically, tacit programming allows you, not theoretically, in practice, we can just get rid of that and get rid of that, and because of the particular semantics of how function application works in Haskell, this becomes essentially a partial function waiting for input. And at the call site, it's determined this argument here is going to be concretized, that's my own word, and be applied that way. In this one situation, where it's literally a one-liner, I'm okay with it. It's not the end of the world. I still feel that it's better to make the data flow explicit. And I've been thinking about this. Why does it bother me so much? And I think the reason is exactly this shape issue, that the only time this is possible, the only thing you can get rid of is the last arg. And that by itself isn't bad, right? That's fine. But what it does is you see people kind of like changing their own APIs from what they would like them to be into this argument is likely to be the thing that's going to be, we're going to drop to make it point free. So let's shuffle that over to the end of the parameter list. And that feels to me like the tail wagging the dog. This, by the way, is another reason why I'm a big believer in a feature that Haskell does not have, which is named parameters. I feel like positional parameters as semantics, I guess I can't call it a code smell. Positional parameters as semantics is a language smell. And yes, we've had positional parameters forever. I mean, they even exist in some sense in assembly language. It's so clear to me that the right answer for function parameters is named function parameters, and you don't care what order they come in. But this is clearly with Haskell and with many other languages, a battle that I have lost. Given a byte string, compute how many UTF-8 characters it consists of. Ooh, Unicode. Data text encoding. Decode Latin, decode ASCII prefix, decode UTF-8 lenient, decode UTF-8 asterisk, tick mark. What's the difference here? This returns an either, and this returns text. This just looks like puts in a character. So we could use this and look for that character, but I feel like either is actually the right thing to get back here. Okay, let's get our byte string. And we're going to be calling, is this qualified, or can I just, data text encoding? It is not qualified, so I just use it. This feels like we want to do this. And what is either? Either is a left error, which we're going to throw away and just return nothing. Or a right, compute how many UTF-8 characters it consists of. A right, we're getting back a text. So, is that right? Well, clearly it's not right. Why isn't it right? Maybe int. That feels correct. Let's see if it is. Looks like it is. And once again, I'm using too many parentheses. I do like that hint. I like that apply this hint key. So I'm getting used to VS Codium. Years and years using Emacs, and I've gone over to a different team. Exercise 8. Given a non-empty strict byte string, generate an infinite lazy byte string. Consists of B, reverse B, B, reverse B, and so on. And then there's an example here. I think the thing we're doing here is using these two different libraries where we've qualified the strict byte string as B and the lazy byte string as BL. And this is something I ended up having to do a lot in some code I've been writing recently. I guess this is the thing about Haskell, is laziness is significant. And the fact that they often separate these libraries into strict and lazy versions means you're often kind of juggling across library boundaries in a way that I kind of wish it was all one library and they just had different function names for strict and lazy versions. But that's not the practice, or it doesn't seem to be the practice. Empty singleton pack. So a lot of this is, these are overloaded in a sense. Like there's a pack and there's an unpack in the strict byte string library as well. So I guess that's why, they don't want to have pack lazy, unpack lazy. It kind of makes sense. It means that if you want to switch from a strict to a lazy implementation, it's a lot easier to refactor if you're just changing your prefix or changing which one you're importing even. We've got this from strict and to strict. I suspect if we're crossing a boundary, we might need those. Basic interface, append head, transforming, intercalate. Is that how that's pronounced? Intercalate. Cycle ties a finite byte string into a circular one, or equivalently, the infinite repetition of the original byte string. And it has no kind of number argument. It's literally take a byte string as input and emit an infinite byte string. Presumably, you'd want it to be an infinite lazy byte string. What's this Haskell stack? I have no idea what this is. Request a call stack. Call stack is an implementation detail. What? This is Haskell documentation at its worst. Like, I've just gone down a rabbit hole into a documentation page that does not tell me what this is. And maybe it doesn't matter, right? Like, I'm reasonably sure that because the library is going to make this transparent for me, but I'm here looking at the documentation and it's got this constraint. So I'm just not going to worry about Haskell stack unless and until the compiler tells me I need to worry about it. But it's a good example of, like, I don't know, man, it's not great documentation, I feel. It's an indication that I don't understand it, and I'm always very uncomfortable when I'm forced to confront things that I don't understand. And we can see that ping pong does not have this Haskell stack constraint. So let's see if we run into it. So we want to emit a lazy byte string, and we're taking a non-lazy one. Take a byte string, return a byte string. Okay, let's call this SBS as our argument. Let's see if that works. What is that going to do? It's already... No, I need to return a lazy byte string, so this needs to be qualified. And it doesn't like it. Couldn't match expected type BL byte string with actual type B.byte string. All right, so here's an example where both of these arguments have to be the same type of byte string, it looks like. Or this is that Haskell stack constraint biting us somehow. So let's do this. We have that BL from strict. And this is not the correct answer. Like, we know that given this argument here, this would just cycle the original argument. But I just want to make sure that compiles. And we should get a test error here. We do. That's great. And that's exactly the error we expect to get in this case. So now, given this, we want to actually create the thing we want to do. B and reversed B. Call that. Let's put a hole there. Right? Found a hole. Needs to be lazy BS. You know what? I called it lazy, so let's call it. Let's get rid of that from strict. So now our hole is of the correct type, I believe. BL.byte string. That's exactly what we want. So we need a reversed version of this. And then this needs to be something like did it again. BL.fromStrict. Something like our strict byte string appended to the reversed byte string, but I don't think append. I think that's a string operation. I don't think that's going to work. From string, from strict. Right, and now it's complaining because plus plus is not. So how do I append to byte strings? Let's go back to the documentation. And now we want these are strict. So I need to be looking at the strict version. No, how do I get back to the strict version? Quick jump, that doesn't help me. Byte string. Append to byte string. It's literally called append. It's just, we don't have the symbol for it. Okay, that's fine. Actually, can I do that? I can, look at that. And it type checks. That's a good sign. Let's see. Let's actually try it. Oops, I still had I forgot to hit save, literally. All right, try that. That looks correct. Run our tests. Great. Well, that was exercises 6, 7, and 8 of set 14A of the Haskell MOOC. You've been watching Tea Leaves Programming. We're programming like it's 1979 with Haskell for Dilettantes. Thanks for watching.